Welcome to the second course of the first chapter of the Smart Data class, Image Basics, Image Filters, and Land Use Extraction. In this course, a more technical side of filtering will be explored. By loading an image into Jupyter Notebook, it can be analyzed, and information can be extracted. Let's start by exploring an image. Since we are still working with GEE, the packages EEE and GEE map again need to be imported. With an interactive map, the following code will be visualized. Let's add a digital elevation model, DEM. The SRTM-90 or NASA Shuttle Radar Topographic Mission provides global elevation data with a resolution of approximately 90 meters. On GEE, we have access to this dataset. By applying certain parameters for the visualization, the DEM shows its full potential. This process of image filtering is essential for successful image analysis. Let's explore this field further by importing a near-infrared composite from data of the Landsat 8 satellite. As soon as the image is loaded, another grayscale makes the visual analysis of the image quite difficult. Therefore, by setting up visual parameters, the grayscale turns into a true color image. Feel free to try out different band combinations to maybe find interesting results. By using the getInfo command, you can discover useful basic information of the imported image, but more importantly, you can see the different variables, such as the band names, to select from. Combine this knowledge with the visual parameters to try out band combinations. Now, we can try smart combinations of bands to explore insights of images. Let's try a near-infrared or NIR image using bands B5, B4, and B3. By making the NIR visible, it is possible to analyze reflectance within a spectrum of light, which is normally not observable by the naked eye. This way, we can look through haze, smoke, and other atmospheric conditions that usually make observations hard in natural colors. By renaming the bands with the following command, we make sure to not get confused with the different bands. Selecting a near band will be less confusing later on. When special events occur, satellite imagery can sometimes help to investigate its cause or consequences. In 2021, a cargo ship blocked the Suez Canal. We can use accessible satellite imagery to investigate this further. First, let's get a new map for this part by using geemap.map. Using the Sentinel-2 satellite images, we can get clear views with high spatial resolution. So, the dataset, here as an image collection, must be imported into the notebook. After importing the image collection, the image location and time must be specified. The incident happened on the 23rd of March in 2021 and lasted until the 29th, which we can use within the filter query. We can use a quality filter to filter down the number of pictures further. This method can also be used to filter out too much cloud cover, which could obstruct the view of the incident. Now, we pick the filtered image with the highest quality, and the first one in the list. As the output of the previous command shows, only one image was left after our filters. This output helps you to determine if you should either apply more filters for higher quality or if you have no choice but to take an image of less quality due to available data. If possible, you could even tweak your filters so that you get more results. After executing the visualization command, a clear image of the incident from the 29th of March 2021 appears on the map. Jupyter Notebook and its Google Earth Engine package also allows including legends within the map to understand its content better. Let's import and visualize some data that can be categorized. Korean Land Cover 2018 provides information about the land cover classes of Europe for the reference year of 2018 with a resolution of 100 meters. With a short command, we import and visualize the data as well as the legend. To extract data from such a combined dataset like Korean land cover, we can use the filter and selection methods. Let's extract the urban land cover of the data and calculate its share for Germany. First, let's select and define land cover as a variable. Now, we use the settlement area, which is code 1112124 in the dataset, as a mask for itself. For that, we can use the GTE, greater than or equal, and LTE, less than or equal functions. Define a variable, urban, that includes all classes within the dataset that are settlement areas. As soon as those areas are selected, we can use this to mask the dataset with itself and remove all pixels that are not classified as urban. After masking, only pixels which have a 1 in the mask remain. Removing the initial layer and visualizing an updated one in red finally shows the urban settlement areas of Europe. To calculate the area within Germany, we need the area of Germany as a scale and boundary. Let's use the Tiger dataset and extract the Germany geometry and calculate its size. With the first command, we make sure to calculate the pixel area of the urban area we already visualized. Afterwards, by masking it with the geometry of Germany, only the urban area within Germany will be taken into account. Now, from the Tiger dataset, we can filter for and visualize Germany. Let's set DE as a filter for Germany. With the following function, we can calculate the sum of pixels in a given area and variable. We define Germany as the geometry for the function. To make this useful for analysis, we needed to calculate the square kilometers within the given area. Finally, printing the area of settlement land cover in square kilometers gives us the numbers we need as a direct output. With the last calculation, we turn the square kilometers into percentages and calculate the difference of settlement land cover to the area of Germany. These were multiple different ways to handle images with Python in Jupyter Notebook using Google Earth Engine. You learned to load images, filter for desired areas and timeframes, visualize them in different ways, and calculate amounts and shares of areas.